In this video, I will show you how to write and graph the equation of a hyperbola, the fourth and final conic section that we're going to learn about. We learned about circles, ellipses, parabolas, and now hyperbolas. Hyperbolas are interesting because they come in two parts. They have two branches, and they have asymptotes. The A value and the B value, we will talk about them more later. But they form this rectangle, and the diagonals of the rectangle show us where the asymptotes are, and the branches approach the asymptotes on both ends. Similar to parabolas, the branches of a hyperbola have a vertex. Each one has a vertex. And so the A value is the distance from the center to a vertex. Now, where with ellipses you have a co-vertex for the B value. A hyperbola technically has co-vertices as well. The co-vertices are here and here. However, unlike ellipses, the co-vertices are not actually on the hyperbola. But that B value is still important because it gives us the length that will form part of the rectangle that we need. Similar to ellipses, hyperbolas have foci or foci. And the C value is going to be the distance from the center to a focus. Now, if you look at the equation of a hyperbola, it's going to be really similar to what we saw for the equation of an ellipse. We have this fraction and another fraction, and it's always going to be equal to 1. But for an ellipse, we always had a plus right here. For hyperbolas, the big difference is one of these two fractions will always be negative. And because of that, we always want to put the positive fraction first and then the negative fraction second. So you're always going to have a fraction minus a fraction equals 1. Now, this distance that I'm going to highlight right now, all right, the length connecting the vertices is called the transverse axis. Okay, so I've highlighted here the transverse axis. So when I talk about a horizontal hyperbola, I'm really talking about a horizontal transverse axis. So here the transverse axis would be vertical. So that's going to affect the equation and which model we're going to use. So if you have a horizontal transverse axis, then the x term for the hyperbola will be positive. If you have a vertical transverse axis, then the y term will be positive. And we will always put the positive one in the front. All right, so if you're looking at a horizontal hyperbola, the x part should be in the front and positive. If you're looking at a vertical hyperbola, the y part should be in the front and positive. Be careful when it comes to these A values and B values. There is something that's similar to an ellipse, but there's something that's different. When we had ellipses, the A value was always connected to the vertices of the ellipse. Now that's still true. The A value is the distance from the center to a vertex, just like for ellipses. The only difference is, for ellipses, the A value was always the biggest. Because the way the vertex was defined, the vertex was always the long way for an ellipse. For hyperbolas, that's not true. The A value will give you the vertex, but it will not always be the longest. Okay? Sometimes the A value will be shorter than the B value. So that's something that you're going to have to get comfortable with. There's one more big change you have to watch out for compared to ellipses. The relationship between A, B, and C. For ellipses, C squared was equal to A squared minus B squared. But now for hyperbolas, C squared is equal to A squared plus B squared. There's one vocabulary word that I left off the list, but I'm going to go ahead and give it to you now. The the distance from one side to the other of the non-vertex side of the rectangle is called the conjugate axis. So you know how the b value is the distance from the center to the side of this rectangle where there are no vertices. All right, so in this picture, okay, so this blue that I just highlighted, that's twice the length of b, because b is the center, from the center to the side of the rectangle where there are no vertices. But the blue that I just highlighted is called the conjugate axis. Okay, let me write that down. Okay, so the conjugate axis will always be twice the length of b. I almost forgot to mention the center. The center is easy because it's the same as we did for circles and ellipses and even the vertex of a parabola. The center is going to be h comma k like it has been for all of the other conic sections. So it'll be the opposite of this and the opposite of this. Okay, so as we go ahead and look at problem number 1, you can probably tell that the center is going to be 0, 0 for this first problem. You can see that nothing is being added or subtracted. There are no parentheses. It's just x squared and y squared. So you know that the center will be 0, 0. At a glance, you should know whether we are looking at a horizontal hyperbola or a vertical hyperbola like this. And it has to do with which variable you see in the front. See how we have y squared in the first term? That means that we are dealing with a vertical hyperbola, a vertical transverse axis. Okay, so just in your mind, right from the beginning, know that we're going to end up with one of these. Okay, now, in standard form like this, the very first denominator, the positive term, is always going to be a squared, regardless of whether it's bigger or smaller. So a squared is 16. That means a is equal to 4. So when I do my plus and minus 4, don't forget that this is the y term. So I will do this in the y direction. So if I go to my center, which is at 0, 0, if I do plus or minus 4 in the y direction, that's going to be here and here. Okay? Now these will be my vertices. So I could write that down right now. Okay, I have a vertex at 0, 4, and I have a vertex at 0, -4. Those are my vertices. Okay, now the covertices, which are not actually on the hyperbola, but I guess we're still going to call them covertices, are going to come from the b value, which in standard form, the b value will always be second. It'll always be the denominator of the negative term. So this is b squared. So that means that b is equal to 3. For hyperbolas, sometimes b will be bigger, so watch out for that. Okay, but notice that this 9 is in the x term, so I'm going to do plus or minus 3 in the x direction. Okay, so I'll do my plus and minus 3 in the x direction. Now these are the covertices. Okay, so that's going to be -3, 0 and +3, 0. So the vertices and the covertices define this rectangle that I'm about to draw. So go ahead and draw the rectangle as a dotted line. Okay, draw the rectangle through the vertices and the co-vertices with a dotted line. So here's my rectangle. Okay, this rectangle is the key to everything. All right, because the diagonals of the rectangle will show us where the asymptotes are. Okay, so the diagonal, now be very careful. Look at the slope of this little segment that I just drew. It's up 4/3. So it will be helpful if I keep track of this. So I will very carefully go up 4/3 again, okay, as I do this. All right, so because you don't want your diagonal to stray off track. So going in this direction, I'm going down 4 and left 3 as I do this. Okay, so I'm going to go down 4 and left 3 again, up, down 4, left 3. So as I draw my diagonal line, I'm going to make sure I hit that point. All right, and I'll do the same thing in the other direction. Okay, so it's down 4, right 3. So here I go with my asymptote. And up 4, left 3, up 4, left 3. So be really careful about how you do your asymptotes. Okay, so look, I could draw my hyperbola branches right now. Because remember, right from the beginning, we knew that this was going to be a vertical hyperbola. Okay, opening up and down. So I can just go ahead and draw my branches approaching the asymptotes. Okay, on this side. Okay, and I'll draw my other branch like this. Okay, got a little janky in there, but good enough. All right, so now we need the foci. So remember that the foci are going to be associated with the c value. And for hyperbolas, we know that c squared is equal to a squared plus b squared, not minus like it was for ellipses. So c squared is going to equal 16 plus 9. So c squared is going to equal 25. Taking the square root, we see that c is going to equal 5. Now, this c value is the distance from the center to a focus. So that means the center to a focus is going to be 5. So I will have a focus here, and I will have one here. So that is 0, 5, and 0, negative 5. Okay, now we need the equations of the asymptote. Okay, so, we need equations for both asymptotes. Now, let's do a quick review on the equation of a line. Now, back in Algebra 1, you might remember something about y equals mx plus b. This is the slope-intercept model for the equation of a line. This is the one that most students remember because if you have the slope and the y-intercept, you could write the equation of the line. So using the y equals mx plus b model, if we had an equation like this, we could easily, if we had a line like this, we could write the equation because here we know the y-intercept is -1, and the slope, well, I don't know why I'm just pointing at that point. The slope, rise over run, right? So this is up 2 over 3. So forget about that. But the I know that the slope is 2 over 3. So using the y-intercept and the slope, if I substitute both of those things in, that gives me y is equal to 2 over 3x minus 1. So that's how that worked. But there's another model for the equation of a line called point-slope form. Okay, and this model is actually going to be more useful for us. And it goes like this: y minus y1 is equal to m times x minus x1. In this model, m is still the slope. x1 comma y1 is any point on the line. So this is going to be a lot more useful than y equals mx plus b, because we don't need the y-intercept. We can just use any point. So if I want to find the equation of this blue line, all I need is the slope and a point on the line. So this point is the point 4 comma negative 1. And the slope is going to be, well, it's down 2 over 3. So that means the slope is negative 2/3. Down to right 3, so negative 2 over 3. So if I have the point and the slope, I should be able to write the equation of this line. Because all I have to do is do the opposite of these two and put them right in here. So just be careful that the y coordinate goes here, but I will do the opposite because of the negative sign. So I will have y plus 1 because of the negative 1 is equal to, now here comes the slope, negative 2/3. Now here comes the x part, so I'm going to do the opposite of the x coordinate, and I'll have x minus 4. And that's it. This would be the equation of this line in point-slope form. It's just that easy. So let's do the same thing to find the equation of this asymptote. So remember, we're doing y minus y1 is equal to the slope times x minus x1. Squeezing it in there. Okay? You know what? We don't really need the parentheses around the y minus y1 part. So all we need is a point and the slope. For the point, let's use the intersection of these two. So we will just always use the center of the hyperbola, which in this case is 0 comma 0. So our point will be 0 comma 0, and our slope, well, it was up 4 over 3. So our slope is 4 over 3. So using the point, if I put the zeros in for x1 and y1, and if I go ahead and put in the slope for m, I'm just going to have y is equal to 4 over 3x. So that's the equation for this asymptote. Now, what about the downward facing asymptote? Well, we're still using 0, 0. The only difference is that the slope is down 4 over 3. Okay, so that means the equation for this line, the slope would be negative 4 over 3. So this is always going to happen. You're always going to have the same equation for both asymptotes, except for one will have a positive slope, and the other one will have the same slope, only negative. So in the end, we could combine these two together, and we're allowed to do this. We can write y is equal to plus or minus 4 over 3x. That's giving us the equation for both asymptotes at once. Okay, and that is it for this problem. All right, so taking a look at number 2. So remember, the first thing we need is the center. So the center is going to be the opposite of this and, well, this. So I'm going to have positive 1 because of the x minus 1. This y squared just means the y coordinate of the center will be 0. Let's go ahead and graph that. So 1 comma 0, that's going to be the center. Next, we need the a value and the b value. Remember, for hyperbolas, the a value is not going to necessarily be the biggest one. In standard form, it'll come from the number that's first, the positive one. So this will be a squared, even though it's a smaller number. So a will equal 2. This is where I will get my vertices. Because the 4 is with the x term, I'm going to do plus or minus 2 in the x direction. So starting from my center, I'm going to do 2 to the left, vertex, 2 to the right, another vertex. So my vertices are -1, 0, and 3, 0. All right, next we need the b value. All right, don't be thrown by the fact that this number is bigger. That happens half of the time for hyperbolas. The b value, b squared, will always be second. It'll always be in the denominator of the negative term. So b is 5. Because the 25 is with the y term, I'm going to do my plus or minus 5 in the y direction. And this will give me my covertices. Okay, so I'm going to go up 5 and down 5. Okay, so my covertices are 1, -5 and 1, +5. Now, the vertices and the covertices define a rectangle. So I will go ahead and draw this rectangle as a dotted line. Okay, the diagonals of this rectangle will be the asymptotes. Okay, so if I go to the corner, this is up 5 over 2. So I'm counting it that way because I'm going to go up 5 again over 2. So when I draw this asymptote, I can be very precise about it. Okay? So in the other direction, it's down 5, left 2. So down 5, left 2 again would be right here. So here's the rest of that asymptote. All right, similarly, the other asymptote will be like this. Okay? So, in all of this excitement, I'm forgetting whether or not this should be a horizontal hyperbola opening to the left and right, or should this be a vertical hyperbola opening up and down? So there's two ways I can remember that. I recorded my vertices. So the -1, 0 and the 3, 0. Okay, that's this point and this point. If these are my vertices, you know, that a value, then this must be where my hyperbola is. Okay, and you've just got to approach the asymptotes. Now, another way to think about it is looking back at your equation. Look at which variable is first. If the x is first, then it's going to be a horizontal hyperbola, opening left and right. So I knew it would open left and right. Okay, we still need to find the foci or foci. And to do that, we need the c value. Remember, for hyperbolas, c squared is equal to a squared plus b squared, unlike ellipses, which had a minus. So c squared is equal to 4 plus 25. So c squared is equal to 29. So c is equal to the square root of 29. That is approximately 5.4, which I will use just for graphing purposes. So, of course, the foci will be in the interior of these branches. So I'm going to go approximately 5.4 from the center in both directions. I went too far. Okay, so from the center, this is 2, 4, 5. No, I was right the first time. Okay, so from the center, there's 2, 4, 5, and then 5.4. So the foci would be about here. Now, when I label these, I can't use the decimal like that. I'm going to have to use the radical 29 version of this. Okay, now, look at the vertices, the center, the foci. They are all lined up together. That means they all have the same y value. And you know what? They're all on the x-axis. So the y value is 0. So we know that for the foci, it's going to be something comma 0. The y value is definitely going to be 0. So I would write that down first if I were you. Now the x value is going to be a little bit more complicated because of the radical 29. Start at the center. The x value is 1. If I start at 1 and I go to the right, I'm adding something. So that's why the x value here is going to be 1 plus radical 29. All right, I'm starting at an x value of 1, and I'm going radical 29 to the right. The x value of the other focus will be 1 minus radical 29, because I'm going to the left. I'm subtracting radical 29. So these are the coordinates of the foci. Now, we need the equation for the asymptotes. Okay, these blue lines. The easiest thing to do is to use point-slope form, which, remember, goes like this. Y minus y1 is equal to, and I'm just putting plus or minus because we have the two different lines here. So plus or minus the slope, and then x minus x1. Now, the x1 and the y1 represent the coordinates of a point on the line. Well, there's one point that's on both lines, and that's the center of the hyperbola. So from now on, I'm going to modify this and say h comma k, because h comma k will be the coordinates of the center every single time. So why not just use the center every single time? So basically, this will be a formula that we could use to find the equation of the asymptotes. Okay, so remember that the center was 1 comma 0. Okay, maybe I'll put this underneath for a second. So the center is 1 comma 0. Now be careful. The y coordinate of the center has to end up here with the y. So that's why I'm just going to have y equals, all right, because k is 0. I need the slope now real quick. So look at the rectangle. It was up 5 over 2, so that's the slope. So I'm going to put plus or minus 5 over 2. And then now the x coordinate is 1. So that's what is going to go right here. So x minus 1. So this represents the equation of both asymptotes. All right, for number 3, we are to write an equation of a hyperbola, and we're given the foci, and we are given the vertices. Whenever they give you some pieces of information and ask you to write the equation, you should draw a diagram for sure. All right, we're told that the foci are 0, -5, which would be here, and 0, 5, which would be here. So those are the foci. And then we are given the vertices, 0, -3, which would be here, and 0, +3, which would be here. So that tells us the center right now, because given the vertices and the foci, we know that we are looking at a vertical hyperbola like this, and because of the symmetry, up 3 and down 3, the center is right in the middle at 0, 0. Knowing that it's vertical tells us which term is going to be first. Because this is vertical, that's the y direction, I know that the y term is going to come first and be positive. So I know I'm going to have y squared over something, and then minus x squared over something is equal to 1. So all I need is the a value and the b value. Well, a squared and b squared. So guess what? We already have a, because a is the distance from the center to a vertex. So a is 3, which means that a squared is 9. And for hyperbolas, the a squared value always comes first in standard form, the positive one. So all that's left is the b value. So look, we have a and we also have c. Since the c value is the distance from the center to a focus, okay, this is my c value. C is 5. C squared is 25. So remember the equation relating a, b, and c. For hyperbolas, c squared is equal to a squared plus b squared. Not minus like it is for ellipses. But c squared is 25. A squared is 9. So that just leaves b squared unknown. So if I subtract 9 from both sides, I get 16 is equal to b squared. And I'm not going to take the square root because b squared is actually what I want. So this is 16. Notice one more time that the b squared value is actually bigger than the a squared value. That's going to happen half of the time for hyperbolas. So with ellipses, the a value was always bigger than b. But that's no longer true for hyperbolas. So this is the final answer. So for number 4, write an equation of the hyperbola with vertices -1, -1, and 7, -1, and covertices 3, -8, and 3, 6. Again, draw a picture. So we're told that the vertices are at these 2 points. So -1, -1. So I've got a vertex here. And 7, -1, which will be right here. So these are my vertices. Now, next are my covertices, which I'm going to do in purple. So 3, -8 is a covertex. And also 3, 6. Okay, we can use the vertices and covertices to find the center. So if you imagine the line, the segment connecting the covertices and the segment connecting the vertices, they are going to intersect right here at the center. So hopefully you can visualize that the center is going to be 3 comma negative 1. All right? This is over 3 to the right and down 1. Also, remember that these red points are my vertices. So that tells me that the hyperbola has branches opening to the left and to the right, because these are the vertices. Okay, so that allows me to write most of my equation right now. Because this is opening horizontally, I know that the x term is going to be first. So when I start off my equation, I'm going to do x in the numerator for the first fraction. Okay, now the center, the coordinates, will tell me what to put inside these parentheses. So because of the 3, I'm going to put x minus 3 squared. Because of the negative 1, I'm going to put y plus 1 squared. So I'm just doing the opposite of each one of these. So all I need now are a squared and b squared. So let's see. The a value is going to be the distance from the center to a vertex. Here's my a value is right here. So this is 1, 2, 3, 4 over. So my a value is 4. That means a squared is 16. All right? The a value, the a squared, will always go first. All I'm missing now is the b value. Well, the b value comes from my covertices. So this distance from the center to a covertex, this is my b value right here. So this is 7. So my b value is 7. That means b squared is 49. So once again, b squared will often be bigger when you're dealing with hyperbolas. For hyperbolas, the a squared will always be first, and the b squared will always be second. So that's it for problem number 4. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.